Page 7 of Properties of Curves. Number 3, consider this function. Show that the derivative is this function and draw its sign diagram. Okay, so all we need to do is find the derivative of f, and it looks like a quotient, so we should use quotient rule. U is 4x, v is x squared plus 1, so u dash is equal to 4. And v dash is equal to 2x. So when we use quotient rule, of course, we're going to copy the quotient rule from the formula booklet. It looks kind of like this. Let's fill in the variables. So v, of course, is x squared plus 1 squared. V on top is x squared plus 1. U dash on top is 4. And u on top is 4x. And v dash on top is 2x. Okay, so let's expand and combine like terms. We have 4x squared plus 4 minus 8x squared on top, same bottom. 8x squared, or minus 8x squared plus 4x squared is negative 4x squared. So we have 4 minus 4x squared. So the top, what if we factored out a 4? If we factor out a 4, the top is going to be 1 minus x squared times 4. And now we could factor a 1 minus x squared. Of course, 1 minus x squared squared is 1 minus x times 1 plus x. Remember the identity, a squared minus b squared equals a minus b times a plus b. So we can use that identity, and the top is going to be 1 minus x times 1 plus x. And the bottom is going to be x squared plus 1 squared. Now it matches, right? Oh, one thing, they have a negative here. So I could get this negative if I reverse these two, right? Because they have x minus 1 here, I have 1 minus x. So I could do one additional step, factor out a negative, and that'll change the order of this binomial. Okay, draw its sign diagram. Okay, so if I draw the sign diagram, I need to put, let's see, at least 2 critical points, because I need to put all the zeros and I need to put all the asymptotes. The zeros come from when the numerator is 0. That would happen when x is equal to 1 and when x equals negative 1. So I'm going to mark those 2 points on the number line. And then we need to make sure that there's no asymptotes by saying, okay, can x squared plus 1 quantity squared ever equal 0? And it's no, right? Because like whatever you put in for x squared, it's going to end up being a positive number, 0 or greater. And so 0 or greater numbers plus 1 is always going to be a positive number 1 or greater. And so there's always going to be a non-zero number on the bottom. So we don't need to mark any asymptotes. And now we're just going to mark the negative 1 and 1 is zeros. And then if we put in the critical value, or not a critical value, but a important value of 0 into the x's, we'll get negative, and then we'll have negative here, and then we'll have positive here, right? Because if we put 0 here and 0 here, we'd have a negative and a positive. So that would give us a positive number, right, if we put 0 in. So that means all the numbers between negative 1 and 1 are going to yield a positive value in this derivative function. If we put in a really big positive number, then the bottom is definitely going to be positive, and the top is going to be negative, and then this would be positive, and this would be positive. So be negative. And then if we put in a really big negative number, then the bottom's going to be positive, and then this is going to be negative, and this is going to be negative, and this is also going to be negative. So it would be 3 negatives times each other, which would yield a negative 2. Okay? So basically increasing between -1 and 1, and otherwise decreasing. Okay, hence find the interval. Oh, now it asks us to find these intervals. So -1 to 1 would be an increasing interval, and then the other two intervals, which would be x is less than -1, is decreasing, and also x is greater than 1 would be decreasing. Okay, so we can see that on the sign diagram, and we could write it out using these phrases. Okay, number 5. So in this one, looks like it's very similar. We're going to start with a function. We're going to find the derivative and show that it looks like this. We're going to draw the sign diagram, and then we're going to find when the function is increasing or decreasing. So very similar. So first we're going to take a derivative of the function. So looks like a quotient again. So the top is u and the bottom is v. And then we're going to write out the quotient rule, copying from the formula booklet. And we know that the u is this big expression. U dash is going to be -2x plus 4. V dash is going to be equal to just 1. And so now if we fill in our quotient rule, the bottom is going to be x minus 1 quantity squared. The top is going to be x minus 1 times u dash. U dash is -2x plus 4. And then it's going to be minus u, which is this huge thing, times v dash, which is 1, and we're done. Okay, now we do need to make it look like this somehow. So it looks like the top is going to become a quadratic that factors into two nice binomials. What are we going to do now? We're going to do a shower or FOIL here, and then we're going to combine like terms with the other part of the quadratic. So if we do shower to this here, let's see, we'll get -2x squared. We'll get -4. We'll get positive 2x, and we'll get positive 4x, which would give us a 6x, right? Okay, so that's part of our result. And then we could distribute the negative sign to all these, and that would give us plus x squared minus 4x and plus 7. And then we can combine like terms. The x squareds go together, the 6x and the -4x go together, and then -4 and the plus 7 goes together. So let's add these up. -2x squared plus x squared would give us -x squared. Positive 6x minus 4x gives us positive 2x. And then, let's see, -4 plus 7 gives us positive 3. And do we need to factor? We still need to factor. So let's factor out a negative sign first, and that would give us x squared minus 2x minus 3, x minus 1 squared. And then let's see, negative, and we'd have two binomials. I think it's going to be 3 and 1. Looks like this one's going to be negative and this one's positive. Yes, it works. -3x plus 1x. Yes, that gives me -2x. So worked. Okay, and then the bottom's going to be x minus 1 squared. Okay, and then so we got exactly what they have here. Remember, feel free to use quadratic formula if you're not good at factoring. Draw a sign diagram. Okay, so let's draw the sign diagram. When we draw the sign diagram, we just need to mark a few critical points like 3, like -1, and like 1. In the case of 3 and -1, they are zeros. So I'll mark them with zeros. In the case of 1, it is an asymptote. So I mark it with a little dotted line. Now I need to check this interval, this interval, this interval, and this interval to see if the whole interval gives a positive or negative f dash value. So let's put in first a huge negative number like negative 100. If we put negative 100 in, we're going to get minus negative number times negative number times negative number squared. So the negative number squared becomes positive. The two negatives multiplied times each other get positive. And so basically the result is a negative number here, right? What about a number between negative 1 and 1? 0 is a very convenient number between negative 1 and 1. If we put 0 in here, we would get a negative number, a positive number, divided by a negative number squared. So that would be negative on top, positive on bottom, and of course we have this negative here. So that would be positive. Let's put in a number that is between 1 and 3. I think 2 is a good one. So if we put 2 in here, it would be negative 2 minus 3 times 2 plus 1 over 2 minus 1 squared. So this is going to be negative, this is going to be positive, and this is going to be a positive squared. And so it's going to be two negatives, multiply those two times each other, gives you positive. So it would be positive. Last one, if we put in a big number like 100 or something, if we put 100 in here, it would be negative times a positive 100 something times a positive 100 something divided positive squared. So this would be negative, okay? So here is our sign diagram. Now it says to say which intervals are increasing and decreasing. So I'm going to write the increasing one in green. It would be this interval and this interval. It would be negative 1 is less than x is less than 1 is increasing. And also 1 is less than x is less than 3 is increasing. And then the decreasing ones would be over here, which would be x is less than negative 1, decreasing. And then x is greater than 3, which also would be a decreasing. Oops. Decreasing. Okay. All right, and that's it for number 5. Now we're going to talk about stationary points. What is the value of f dash at a stationary point? So do you remember that a stationary point is a point where you can balance a ball exactly on the curve and it won't roll away? So that happens at maximum points, it happens at minimum points, also can happen at stationary inflection points, okay? But basically, at the slope at any of these points, the reason why the ball doesn't roll away is because the slope is 0. Okay, what are the 3 types of stationary points? It would be local maximum, local minimum, and stationary inflection point. On the graph below, mark the global minimum, the global maximum, the local minimum, and the local maximum points. Okay, so let's do that. So in this graph here, I'm going to mark the global maximum. It's this endpoint here, right? That's the tallest, the highest point. Is this a stationary point? No, because it's not a place where the ball would balance, okay? This here would be a local minimum because it's a stationary point and it's also a minimum in its general neighborhood. Right here would be a local maximum because it is a stationary point and in its own little neighborhood, it is the highest point. And finally, this endpoint here would be the global minimum because this is when the function is at its lowest in the interval shell. Okay? All right. Is the vertex of the parabola y equals x squared a global or local minimum? Okay, so remember, if you have a parabola, it goes infinitely upwards in both directions and never goes down. So the vertex itself is the lowest point, and it is a global minimum because there's no other points that are lower. It's also a local minimum because at this point a ball would balance, and it's the lowest point in its general neighborhood. So it's actually both. At the right, we see the cubic function y equals x cubed. Mark the point on the function where the derivative is 0. Right there, right? This is where the ball would balance. The derivative of 0, it's a stationary point. It's neither a minimum nor a maximum. What kind of point is it? It's a stationary inflection point. Stationary because the derivative is 0 right here. Inflection point because to the right, the curve curves up, and to the left, the curve curves down. Okay, so it's kind of in between being a maximum and minimum, and so it's an inflection point. Remember, when you look at a curve from the top, the inflection point is kind of where you would see the point where a car that is turning right starts turning left. That is the inflection point. Okay, it's when you stop turning right and you start turning left, or vice versa. Okay, so that's what an inflection point looks like. The definition, the math definition of an inflection point, you could say that it is where the second derivative is equal to 0. Okay, all right. So now we're on page 8. Let me end this video.